Okay, so this is a set of notes on tangent planes, right? And the basic idea here is that you have some sort of surface, right? We'll call that z is f of x null, y null. And on that surface, we're going to find a point. So the point P, that should be just z of x, y. Let's make that simpler. The x null, y null comes in later. Z of x, y, and then we have some point x null, y null, z null that's existing on this surface. Okay, so what we want to do is we want to draw a plane that's tangent to this surface through this point. And our argument is going to be that if I take z minus z null is the f, or the x partial at x null, y null times x minus x null plus the y partial at x null, y null times y minus y null. I'm going to get a plane that's going to be tangent to this surface at this point. Now, if you look at this kind of carefully, this is like the extension of y minus y1 is m times x minus x1, the point slope form of a line. So essentially what we've done is we've taken this thing and we've ramped it up. And this gives me kind of some of the idea here, that this is still the height, the change in height. This is the change with respect to x. This is the change with respect to y. This was just the change of y with respect to x, right? So this is change of height with respect to x, change of height in respect to y. Basically what we're doing here is we're building a weighted mean with the change of x and the change of y with the two partial derivatives. So it's kind of a way to understand what's going on here. We're going to verify that like the math here actually works. And we're actually going to work from the point slope form to show that. Okay, so if you use the point slope form with x and z, you're going to get z minus z null is m1 x minus x null. So that's going to give me something that passes through the point x null, y null, z null that's tangent to the plane. And in this case, it's going to be parallel to the xz plane, right? If I do the same thing and I take z minus z null is m2 times x minus, sorry, not x this time, it's y. Y minus y null. I again get a line that is tangent to our surface that goes through the point x null, y null, z null, and this time it is parallel to the yz plane. Okay, so it is, since these are lines that are not going in the same direction, we're assuming that m1 and m2 cause these lines to actually intersect, right? Two lines that intersect will actually determine a plane. And what we simply do is, in our little model here, we let m1 be the derivative with respect to x at x null, y null, right? We let m2 be the derivative with respect to y at x null, y null, right? And the idea here is that if you do this, we're now going to say that we're going to do like a linear combination here, right? Z minus Z null is the linear combination of these two things, f of x, x null, y null, times x minus x null, and add f sub y, x null, y null, at y minus y null. All right, so let's take a look and think about this. If you force this thing so that if y is equal to y null, right? So if you force y equal to y null, then this piece here becomes 0, right? Because y null minus y null is 0. So we get back z minus z null is fx x null y null, x minus x null, which is this line, right? So it's this line. There we go. That one, right? And if you fix the x value now, so we're going to fix the x value as x null, right? Now we get something very similar, but this becomes 0 because x null minus x null is 0, so that falls out. We're going to get z minus z null is fy x null y null, y minus y null, which gives me that equation. Now, so we've got it to reduce to the two equations, right? So this tells me, in fact, that this line and this line are parts of this plane. So that means this is the plane that is determined by these two lines. These two lines intersect at this point, right? So there and there, which means that I have the unique tangent plane to the surface given in this equation here, right? So this equation here, well, the muck around it, is the equation to the tangent plane to the surface at this point. So, like, this is kind of messy at this point, but let's look at an actual example. All right, so let's look at an example. All right, so let's say I want a plane that's going to be tangent to z equals 2x squared plus y squared, and I want to do this at the point 1, 1, 3. It should be pretty clear that if x and y are 1, z comes out as 3, so that's definitely a point that's on this surface. So the first thing I need to do is let f of xy be 2x squared plus y squared. And then I need to take the two partials. So let's take the partial with respect to x. Gives me 4x. So the partial with respect to x at the point 1, 1 is just 4. And then we take the partial with respect to y, which is going to give me 2y. And the partial with respect to y at 1, 1 is going to be 2. So let's see. I need z minus z null, which is 3. F sub x gives me 4 times x minus x null is 1 plus f sub y is 2 times y minus y null is 1. So a little bit of work here. I can distribute the 4 and the 2. Right, it's going to give me 4x minus 4 plus 2y minus 2. Right, combining some like terms here. I think I'm going to get z is equal to, let's see, that's going to give me 4x. That's going to give me 2y. Negative 2 and negative 2 is negative 6 plus 3 gives me negative 3. So this plane, or this plane, yep, is going to be tangent to that surface at that point. All right, so that's pretty straightforward. There you go. And we'll work with this in class a little bit.